Hello and welcome to part 5. Right here we're showing a demonstration of dead time. I normally have a 3 ohm resistor for a load, but I have a little 270 ohm resistor in series, and I can short that out with a switch. So right now the 270 ohm resistor in series, so it's a very light load, and I'm turning this on as hard as it'll go. And this is a demonstration of the arc interrupt. And so what happens is this low section right here, that's when the FETs are on. So that's about 10 milliseconds, 9.8 something. And this part here is where the FET turns off. This simulates operation at like 50 hertz, which most thermostats are rated at. And it allows you to open the contacts, and the arc cannot possibly last any more than 9.8 milliseconds. Typically it'll be much shorter than that. So this is what we're doing. Here your FETs turn on. This is your thermostat. This is your heating element. And so every 10 milliseconds we're turning off the heating element. And what you hope to do is you want that frequency, the cycle for the PWM, to be as long as possible. And 50 hertz is what people are used to. So switches and stuff are designed for that. Like 9.280 is the minimum, it's the longest time that the FETs are allowed to be on. So during that time, the switch opens up, there can be an arc, and then after that, the FETs turn off. You have 720 milliseconds for the arc to quench. And that is done by, there's a dead time resistor. I'll show you where that is. It's 100 ohms as it comes from that board from the factory, and I increased it to 220, and that's now 7.2% dead time. So you want to design your whole system that in normal operation PWM resets before that. What that means is you have your capacitor bank charged, and you want to hope you drain it down before you ever get to the arc interrupt, and that'll be the most efficient way possible. And you do that by taking the heating element and making it a little lower resistance than ideal. So that means the heating element can draw more power than what your panels can produce. So that's it. That's how arc interrupt works. Now, this thing works so good. What I have is a ragtag collection of capacitors here. These are junk. These two over here, one's a 3300, the other's a 4700. They're 50 volt. The rest are between 100 microfarads and 470. So we've just slapped as many on as we can. Each capacitor will be supplying some current. So with this load resistor, anytime it turns on, you're pulling 13 amps. So I have a power supply up here, and you can see it's set around 42 volts. I simulate a solar panel with a 1 ohm resistor and a diode. I don't want to be messing with the power supply too much. I want to isolate the capacitor bank from that. And this is as it's built. It's cute. The FETs don't get hot. Everything fits here. There's some junk underneath. One of the new things this is the 1 UF capacitor. I really now don't suggest you replacing this with this 0.1 UF capacitor. I was really intent on building this with a using the shutdown pin to turn everything on and off. So basically the oscillator would free run, it would be on all the time, and you'd control the shutdown pin, and you would add cycle by cycle for the whole thing. But that doesn't get you arc interrupt. And I was thinking we're just going to do low voltage here. But damn, this thing works so good. Now, a year or two from now, you might have a few of these capacitors blowing up. That's the reason you don't have a 9-volt transistor battery starting your car. You know, it takes space to do energy storage, and if you want things to last a long time, you have to over-design. One thing that's unique about me is I come from the world of repair. I started out, my first job was when I was 14. I was repairing electronic organs. And that was back when, if you knew anything about electronics, the world was your oyster. People would let you do anything. Can you imagine trusting kid 14 years old, to work on a $5,000 organ? And like $5,000 in 1964 was a lot of money. But some people trusted me. It was their only opportunity. So I've always loved repair. You know, it put me through college going through repairing audio equipment. Fortunately, I worked for high-end audio places that people were willing to pay a lot of money. I mean, I could make $300 on a weekend coming home from college. I knew Saul Morantz. Funny guy. And so that taught me a lot about failure. You know, one thing the Chinese learned is you can get almost anything to work for a year. And by that time, it's too late for you to get your money back. And you're thinking, well, maybe it was just bad luck. But really, things are just bad design. So I wanted to go higher frequency, and you can still do that with this board. As the little pot here, it's a 20K pot, and it's set at about 16K. And that's 50 Hertz or 100 Hertz in the PWM, because we're doing half cycles. So if you turn that pot, and it's easy because you know, you got a ground connection and you got pin number 6, it's easy to just go across the pot. Adjust that till you get to 8K, then you'd have 100 Hertz or 200 Hertz PWM for the and like you can go down to 4K, and that gets you up to about 400. So there's really not much of a reason. I was thinking that I'd be turning this thing up to maybe 2 or 3, 4, 5 kilohertz, doing cycle by cycle shutdown. But this kind of works real nice, and at 50 hertz, you really have to do 50 hertz if you want to do arc interrupt. Otherwise, you don't have enough dead time. And it's not a percentage. You have to have 500 microseconds of time. So if you're doing, you know, low voltage, you're not that much worried about the arc. So if you're under 60 volts, somewhere around 60, 70 volts, you could put a 180 ohm resistor in there, and you'd have around 500 microseconds of arc interrupt, which is enough. If you get over 60 volts, it's probably good to have that little extra time in there so the arc cools off enough to that it won't come back. But I'll tell you, I'm really impressed with this thing. Remember, that load resistor is 3 ohms. You're putting 40 volts into it, and it's running really nice. Now, the other thing that's really new is normally on one of these IRF3205s, you have a capacitor. It's a compensation pin that slows things down a little bit. In power supplies, design of compensation is pretty elaborate to give you really fast response. Here it doesn't really matter. Here it just makes it stable. Now that pin 9 coming up, that's just a pin. There's no pad or anything, but you have a nice pad around here that's ground, and if you have one of these little capacitors, you can run it from here to there, and as long as you're careful soldering, it'll work fine. But you know, if you're not used to soldering, it'll work without it. It'll be just a little more unstable. So now let's flip this switch, and I'll get down to a little lower speed. So this turns on. About all this capacitor bank can hold is 100 microseconds of energy. Not a lot. That's why you want to go big. But as you can see, I have this thing set up for around 1.5 amps. And this is a full 40 volts here. It's dipping down a bunch. I want to show you something really kind of interesting. Take a little second. Okay. I have a current meter here. So let's get that in there. And it says 1.4 amps. That's the average. I found that these are really good. When they're measuring pulse DC, it's a real good average. So it's 1.4 amps there. Now going in, what do we have? 1.4 amps. Like I say, it's pretty efficient. And look how clean that is. If you don't have the comp pin, you may have some other false triggers in there once in a while. But this system really works. And it even works with a really crappy capacitor bank. But, you know, put as many capacitors as you can in, and, you know, a year later or 2 years and it blows up, you might be willing to spend some money on some good capacitors. The ones I use, you know, that system would be running 20 years from now. You know, there aren't bad capacitors, they're just bad designers.